Okay. So welcome back again. This is sort of going to be the last of what you might call the foundational lecture series part of the school. After this, we are going to delve deeper into very specific themes. But this is the last broad theme that we are going to explore. And this is one theme that we'll dig deeper into towards the end of the school, but this is perhaps a good time to talk about it and give you an introduction, because must say that the first day has been somewhat biased in only showing you really nice positive results, efficient algorithms for a lot of problems. Although I guess you did see one example of an algorithm that clearly doesn't have a FPT algorithm. Anyone know which one? I think it was in the first lecture yesterday morning, which must feel like ages ago, but there's like this one problem. Max something. Max 1. Number of ones. Can you set, or was it just max set? Can you? No, max ones. Maximum number of ones. Okay, all right. There was also a parameterization by the length of the clause, if you remember, which was hard, because you know that even when the clause length is a constant, the problem is NP complete. So if you parameterize by such a thing, then clearly you don't expect a FPT algorithm, because if you have a FPT algorithm, then you try to use it for 3-sat in particular, for example. If you're just trying to satisfy, if you're just asking satisfiability, right? It's a simple question. Can a formula be satisfied? Parameterized by the length of the longest clause. Okay. Here, if you just have a FPT algorithm, apply it for something like 3-sat, and boom, you have a contradiction. You actually contradict the conjecture that P not equal to M. Okay. So that's a very strong kind of a hardness remark. Because notice that not only does it mean that you cannot have a FPT algorithm, it means that you cannot have any algorithm of the form n to the f of d, where d is the length of the longest clause. This is not even FPT. It's worse than FPT, because remember, FPT is where we try to separate the function of the parameter from the exponent of the input size. So in FPT, we are typically looking for f of k times or plus poly m. So this is not even FPT, and you don't even expect this for something like satisfying formula parameterized by the length of the clause. So that's a very strong hardness result in some sense, saying that you don't even have what's called a XP algorithm. Forget about a FPT algorithm, okay? But there are lots of problems that do have easy XP algorithms, okay? Can you think of some? K-size clique. Parameterized by the number of variables, there the parameter and the input size kind of merge it. I don't know how to put it in this format necessarily. But okay, let's say clique, for instance. Do you have a clique of size at least k? Okay. N to the f of k is kind of obvious, because you can just try all possible subsets of size at most k. So that's clear. What is not so clear is, can you actually achieve this kind of a separation in the complexity? Okay. So there are problems which are XP, for which nobody has been able to come up with a FPT algorithm. And the question is there a deeper reason for that that goes beyond our incompetence? Maybe there's something more going on. So that's the kind of thing that we want to explore here. Like I said, during the first day, you would have probably gotten the impression that you just have to pick a NP hard problem and just work away at finding a FPT algorithm, fix a parameter, and just sweat it out to get a FPT algorithm. But for some problems, we are going to see that they actually probably don't have FPT algorithms. And the reason this kind of knowledge is useful is because you don't waste your time trying to find a FPT algorithm that's very likely not even there. Okay, so that's the usual incentive for doing hardness results. Even in the classical context, the reason when you have a problem which is mysterious, you don't know if you have a polynomial time algorithm or not, you might exhaust your polynomial time algorithmic toolkit, But once you sort of have roadblocks all the time, you go back and ask yourself, well, maybe this is NP hard after all. And then you go back and forth, and it's useful to establish hardness early in the day so that you're not spending a lot of pointless time coming up with an algorithm that, again, is probably not there. So, all right, so far we've seen a bunch of examples for problems that are FPT. So this is what I just said. You typically do stuff and make it FPT. But for a lot of problems, you don't expect this. And we're going to start with the assumption that clique is such a problem. So this is the global picture, by the way. This is FPT. And this is the zone that we are going to explore in this talk. Okay? So we're going to assume that clique is such a problem for which you don't have a FPT algorithm, maybe because of the overwhelming evidence that a lot of smart people in the last 20 years haven't been able to come up with an FPT algorithm for clique. There is a more technical reason for this, however, which we will see in a future lecture. We will try to at least understand a bit of why we don't expect clique to have a FPT algorithm. It's not quite as simple as saying if clique has a FPT algorithm, then P equals NP. We wish we could say that. It'll make it really kind of clean, but it does imply something which is also believed to be sort of unlikely. Okay? We'll come back to that for the purpose of this lecture, which is kind of going to be a lighthearted, fun excursion in hardness reductions in this kind of context. We're just going to assume that clique, when parameterized by k, is unlikely to have a FPT algorithm, so it's in this zone. With this assumption, what more can we say about other problems that we regularly encounter? Okay? Let's just go over the notion of a reduction. Typically, you're stuck with a problem for which you're trying to find a FPT algorithm. Maybe some of them are in your problem sheet. I don't know, are there any trick questions? Probably not, okay. So you've been assigned a problem to solve, and you have this big toolkit of FPT algorithms all the way up to the last lecture. You're trying to solve this problem, and you get stuck, so you sort of decide that I'm going to prove to the world that if I cannot solve this problem, nobody can solve this problem. That's the usual theme of a reduction, right? So now you know, for example, or I'm promising you that there is no FPT algorithm for clique, let's say. Then what you can do is, if you're not able to solve the problem, so it's the saying, if you can't defeat them, then you join them, right? So if you can't solve your problem, you try to give a formal proof that if somebody can solve your problem, then you can solve clique, which would then be a contradiction to common knowledge. Okay? So typically it goes like this. You come up with an algorithm that looks like this. Okay? It's sort of a subroutine for solving clique that uses an assumed subroutine for solving your problem. Okay? So you say, hey, suppose you give me a FPT algorithm for my problem. That's this FPT algorithm. You give me that. Then here I have this thing here which is going to solve clique in FPT time once you give me this. Okay, so that's the flow of the argument. Let's formalize it just a little bit. Okay, let's look at an example first. Here I'm staring at an instance of independent set. Okay, and I want to say that, well, independent set is unlikely to have a FPT algorithm as well. And can you see why? You would just complement the graph. You would say, okay, here is my subroutine. If somebody can solve independent set in FPT time, then I'm going to use that algorithm on the complemented graph to solve clique. Okay, the complement clearly has a clique wherever there was an independent set in the original graph, right? So that's the kind of the logic. Okay, but let's try to formalize what this subroutine actually is. So it's typically called a reduction. Okay, what it does is it starts with an instance of a problem that's already believed to be hard, and now you actually have two problems in that set. You have clique, and you just proved independent set also shares the same social status. So now, so you start with some problem which you know to be hard. So that's this guy out here, and you try to write this algorithm, which is going to mold that instance into an instance of your problem, on which you can then apply a subroutine that somebody gives you for your problem and then derive the contradiction. Okay, is that making sense? All right, what properties should this algorithm have? To get the contradiction, you want to say, so what is the heart of the matter? The heart of the matter is that if this was a FPT algorithm, then this whole thing is a FPT algorithm for clique. So first of all, this blah, blah, blah has to happen in FPT time. If you spend more than FPT time, then your proof doesn't work. Okay? So we need that in the definition. The reduction itself must be FPT time. Okay? Now, after you reduce, you get this instance x prime k prime. Okay? And to sort of really put the last nail in the coffin, what you need to do is run a FPT algorithm on this instance that you generate. So somebody has given you a FPT algorithm for your problem. You need to run it on the instance that you generate. And when you run it, it has to be FPT. Okay? So in particular, the time that you spend on this instance is going to look like this. Because somebody has given you a FPT algorithm, the time spent is going to look like f of k prime polynomial in the size of the instance. Now, this has to be FPT in the original instance, right? Because that's what you need for the contradiction. So for this to be FPT, f of k prime must in particular be a function of k, which is the original parameter. In particular, this means that you cannot make k prime a function of n. Okay? K prime is constrained to be a function of k alone, so that k prime is some g of k, then f of g of k continues to be a pure function of k. Then you get a FPT algorithm for the original problem, and that will finish off your contradiction. So in the definition, we need to have this. The parameter of the output is a function of the parameter of the input. Okay? So this is our basic notion of a FPT reduction. You start with an instance of a FPT of a parameterized problem for which you believe there is no FPT algorithm. If you're able to reduce it to your problem in this specific fashion, then you know that your problem is at least as hard as that guy. Okay, so at least it joins the club. So, and then that is sufficient evidence that it also doesn't have a FPT algorithm. Okay, so any questions so far? Okay, so this is our working definition of what we call a FPT reduction. Let's look at this sample reduction just to test our understanding. Here is my problem. It's vertex cover. It's a very familiar problem by now. And vertex cover has a standard NP hardness reduction from independent set. Okay, is this a FPT reduction? No. Because you've seen FPT algorithms for vertex cover. But is there another reason? Yeah, so what's screwed up here is that this guy is not a pure function of the original parameter. It started depending on n, so that proof that you would have for inferring the hardness of vertex cover breaks down in the last step. Okay? So when you try to run a vertex cover algorithm to solve independent set, you have a 2 to the k algorithm for vertex cover, but when you try to run it for this instance, it becomes a 2 to the n minus k algorithm, which is no longer a FPT algorithm. Okay? In particular, this establishes that not all NP hardness reductions are automatically FPT reductions. And that's, in fact, at a big picture level, that's a lot of the reason that we do parameterization is because it gives us a finer classification of the problem space. Because if every NP hardness reduction was FPT reduction, then all problems would be equally hard, even in the parameterized setting. The whole point is that, well, some NP hard problems are hard in the parameterized setting, but some of them are easier. And that difference is illustrated very nicely in the vertex cover independent set sort of dichotomy. So independent set is hard. Independent set and vertex cover are both hard in the classical setup, but one of them is significantly easier than the other in the parameterized setting. Okay. Are all FPT reductions automatically NP hard reductions? Let's just go back. Yes. Okay. So here. Okay, the second condition makes a FPT reduction more restrictive, okay? And that's why some NP hardness reductions break down. But the first condition actually gives a FPT reduction more freedom, okay? What is the difference between this requirement and the requirement in a classical reduction?
That has to be polynomial time.
Exactly. A classical reduction is obliged to run in polynomial time. Otherwise, you don't get NP hardness for the same reason. Okay, because for the contradiction, you need the whole reduction to run in polynomial time. Otherwise, you cannot infer hardness. But here, you have more flexibility. You can actually spend more than polynomial time to arrive at your solution. So not every FPT reduction is an NP hardness reduction.
So even the size of X prime could be FPT size, right?
X prime could be FPT size. Is there anything on the slide contradicting that?
No,
Sorry.
no,
Okay. All right. Yeah. X prime. So once you spend FPT time generating the instance, you could potentially be generating a fairly large instance. But polynomial in X prime is still going to be FPT in the original guy, which is a good point. Yeah. So he's saying that the size of X prime could potentially be something like f of k poly n. And then when you run, I think, let's see, yeah, it won't be an NP hard reduction in particular, but when you run this algorithm, this factor here is polynomial in X prime. So it's poly of f of k poly n, which is, it's not polynomial. The running time here is not polynomial in the size of the input, but it's still FPT in the size of the input. So there's no danger in turning X prime into a FPT sized object, but there is a danger if you allow K prime to start depending on n, because that will destroy the FPT-ness of this running time more seriously. But here you're okay, because poly of f of k in particular is going to be this still has the required format. Okay, so if the size of the instance blows up, it's still fine, because all you want is to be able to work in FPT time down here. You don't need this algorithm to be polynomial time at all. You need it to be FPT time.
Is it possible that for a different choice of parameter you have FPT?
Sure. So this is very, very parameter specific. The same problem parameterized in a different way may have a completely different complexity setting.
So FPT reductions are not NPR reductions.
Correct.
Okay.
I didn't really understand the inference you're trying to derive by saying, so is it okay to have a larger instance?
It's okay to have a significantly larger instance spewed out by this reduction.
But K prime has to be smaller than K, right?
K prime has to be a function of K.
Okay.
Yeah.
K prime has to be a function of K.
And it's okay, as long as K prime depends only on K.
Every time we try to apply FPD algorithm or something,
Yeah.
we try to derive a smaller instance, right? And
Oh, I think probably overlapping this slide with the kernelization slide. This isn't about getting a smaller instance at all. This is just about saying, this is just about revenge, right? If I cannot solve it, you cannot solve it. It's just that sort of a connection that you're trying to establish between two problems. You're not trying to do anything useful here, other than convincing yourself that you don't need to be ashamed about not finding a FPD algorithm. That's it. Nothing about making things smaller or efficient or any of that. When a reduction works in reverse, you have to worry about those things because you're trying to actually use an algorithm for some problem to solve your problem, but that's a different setting. Okay, so here you're just going the wrong way. Okay, so questions? Okay, so it's not obvious that FPT reduction is NP hardness reduction. It's certainly not automatic from the definition, and indeed there are examples where you can exploit this freedom in the definition to get stronger reductions which don't automatically project to the classical setting. And here's a trivial example. So suppose you're interested in finding a clique on at most log n vertices. Okay? All right. So this problem has an algorithm. What's the running time of the brute force algorithm for this problem? N power log n. Okay, and just take it as a fact that algorithms, problems that have n to the log n kind of algorithms are not expected to be NP hard in general. Okay, so this is a problem that we don't expect to be NP hard, but you can still reduce it from clique. Okay, how can you reduce it from clique? So let's say you start from clique. In the sense that reduce it meaning FPT reduce it from clique, and we'll see how the first aspect of the definition actually gives you a leeway that the classical reductions don't give you. Okay, so you start with an instance of clique. Okay, and let's first just try to imitate clique. I mean, this is a very similar problem. You were asking for a clique there, you're asking for a clique here. So let's just say the reduced instance is just the original graph. Damn it. Okay. Okay, that's a mistake. So let's say that the reduced instance was just the original graph. If you have a clique of size k here, you have a clique of size k here. What goes wrong is if you have a clique of size at most log n here, you may not have a clique, you may not be able to pull it back to a clique because for all you know, the demand is much bigger than log n. Okay? So to compensate for that, if the demand,
No, I didn't get the point.
I'm saying that if you have a yes instance here, I mean you're trying to again show the equivalence of the two instances, right?
So if you had a G comma K, you're mapping it to G comma what?
I'm mapping it to G comma K again,
Okay.
just the same K.
Okay.
What is the log?
Here, the log clique problem is supposed to be a yes instance if first of all K is at most log n, and then there is a clique on K vertices. Is that okay?
So it might not be a valid instance itself.
Yeah, I mean, yeah, it may be, you may just reject the instance because K was too big, so you're free to reject the instance. Does that make sense? Yeah, so if K is more than log n, you may say no here because you're allowed to say no for free, right? But when you go back, that's not quite correct because you may actually have a big clique, okay? So when K is greater than log n, again, we'll try to write it the other way. Let's see, one good way of writing this, 2K is greater than n or n is at most 2 to the k. So in some sense, in this setting, you have a small instance here. I guess one way of looking at it is that you can actually solve this instance completely in FPT time. But a sort of more elegant way of doing this is that I'm going to basically push up n to force k to be smaller than log n, so that I actually have a serious clique sitting here. So basically in this reduced instance, what is the work that I have to do? I'm damn close, okay? So if there is a clique here of size k, there's definitely a clique here of size k. And in the reverse, if k is less than log n, I'm fine, because if k is less than log n, this guy has to find a clique of size k, which I can just pull back to the original instance. But if k is more than log n, I somehow want to make this guy feel obliged to find a clique anyway, okay? So what I'm going to do is I'm going to increase n so badly that I'm anyway going to be forced to find a clique in the original graph, okay? So one way to do that is to just add 2 power k isolated vertices out here. Sorry? No, I will not need 2 power n. Let's just see why this works. So what is my n prime? It is n plus 2 to the k, right? So if k, now the k here is definitely at most log n, log of n prime. Is that clear? What is log of n prime? It's, I mean, it's definitely, yeah, I mean, it's, yeah, I mean, sure. Log of n prime is at least log n, so yeah, this is okay. So once you add isolated vertices, they're never going to participate in any clique. So now you've sorted out the issue of k being potentially bigger than log n. K cannot be bigger than log n if n has a 2 to the k sitting inside it, right? So n is 2 to the k plus something. So k is never going to be more than log n. It's at most log n. And then the instance here cannot hope to find a clique in this region. It's just a bunch of isolated vertices. So it has to find a clique of size k, and it has to find it in the original instance. Okay? Does that make sense?
But then you're changing, it's not G and it's G prime.
Sure, it's G prime. That's a typo. It's kind of H comma k, if you like. That's right. It's a new graph. It's a new instance. And all you needed to do was really to fix this issue of what happens when k is too big. Well, then you blow up n so that k cannot be too big in terms of the original parameter. Okay? All right. I guess another way of looking at it is that the case that's problematic is when k is more than log n, but in this case n is at most 2 power k, and the entire instance is bounded. So you can actually spend fpt time solving the instance, find a max clique, it will take you 2 power 2k time. Find the max clique. If the size of the max clique is more than k, is at least k, then you return a trivial yes instance. Otherwise, you return a no instance. That's another way of doing it. Okay. Either way, you know that you don't expect to have a FPT algorithm for the log clique problem parameterized by k. However, this is evidently not an NP hard reduction. Yeah. Because you're using a lot of freedom here. You're spending 2 to the k time adding vertices, or in the other approach, you're spending even more time in solving the problem. So you're not allowed to do this in an NP hardness reduction. Okay? So this is sort of an easy example of a problem that admits a W hard reduction and is not expected to admit an NP hard reduction because it can be solved in n to the log n time. Okay. The more interesting non-contrived examples, if we get time towards the end of the lecture, we'll at least see a glimpse of one such. Okay, so this is the other takeaway. So just, I mean, if you don't remember anything else, you might just want to remember the notion of NP hardness reduction, and remember that they're not directly comparable to NP hardness reduction. Some NP hardness reductions may not be FPT reductions, and the other way around. Okay. All right, so let's look at a canonical hard problem. I mean, I did say clique is what we're going to start with, but here's a formulation of clique that's very, very useful for starting reductions from, because it puts it adds some structure which turns out to be very useful for reductions. And again, hopefully we will see an example of why this is kind of handy. But let's explore the problem itself first. So you guys remember a colorful path from yesterday's lecture, post-lunch. So the idea was that you're actually given a partition of the graph into k parts, and you want the structure that you're trying to identify to intersect each of these paths at exactly one vertex. So you want whatever it is that you're trying to find should be kind of evenly spread across these paths. So that's colorful path, and colorful clique is kind of similar. So you essentially, your graph is partitioned, and you're trying to find a clique that cuts across. Okay, and I think this did come up yesterday. You wanted to know if you can do some dynamic programming or something like this to solve this problem, but if you start with the belief that you cannot solve clique, we'll actually see that this is as bad as having to solve clique. Okay. Any ideas? So I give you an algorithm for clique. I give you an algorithm for multicolored clique. Then you want to say that, hey, I can take your algorithm and I can solve clique with this. So you start with an instance of clique. You always start with an instance of the hard problem, and then you try to morph it into a format where you can then just ask the multicolored clique question.
So the vertices that you have drawn red, this is supposed to be single vertices within that component, or just connectivity between components through some vertex or the other?
Sorry?
There's a single vertex, right?
There is a single vertex in each component. Yeah, I think I should put down a more formal definition. So you're given a graph G. I should say G. The vertex set is partitioned into k disjoint paths. Okay, and you're asking, does there exist a clique? Sorry, I'm just coming to you. And S intersection Vi is exactly 1 for all. Okay, sorry, probabilistic what? Okay. Sure. No, but then with high probability, your clique is spread out in the graph, but you still need to find the guy. Oh, you're saying you're giving a reduction. Okay, all right. I thought you were contradicting the fact that it's hard. Sorry, my bad.
Partitions are,
So you're saying
are given.
these partitions are given as a part of the input. You get a partitioned graph.
Randomized FPT
You can get a randomized reduction. All right. Interesting.
What is the parameter
K.
here?
Oh, parameter is k. Thanks.
Size of the click.
Yeah, the size of the click. Wow.
So just a question.
Sorry.
So each of those parts intersect, they get exactly one vertex, and the path is supposed to be colorful.
Not path, it's click.
Uh,
Path is colorful, but what about the colors and PR? The
So-
cliques are properly colored, right?
the clique ends up, if you think of these paths as being colored vertices with different colors, then the clique that you're staring at is properly colored. That's right. So you're given a graph that's partitioned into k parts, and you're trying to see if there is one vertex that you can choose from each part, such that all of these vertices together form a clique. That's sort of the question.
So what's the question?
I just said it. I thought. Okay, sorry. Okay, so even the meta question. The meta question is multicolored clique as hard as clique? Yes, yes, by your randomized and then de-randomized reduction. it's out of my league, dude. No,
No, I can simply shrink every component into one vertex.
sure. I mean, I'm not saying. I'm just saying that it's probably too high level for me.
So,
So no wonder you're looking so nostalgic. All right. No, I'm just saying it's too difficult for me. I'm not saying it's not a reduction. Sorry, yeah, you were saying something.
we need reduction from clique to this clique.
Correct. You need to start with an instance of clique, and this, huh? Correct. I'm looking for FPT reduction. Yes. So I think the suggestion is to randomly color the graph, right? And with high probability, so you're starting with an instance of clique. It doesn't have these partitions. So you're trying to convert it into a graph that has partitions, and somehow you don't want to use any additional resources. I mean, you don't want to bring in more vertices or anything. So you want to stick to the same graph. So you partition this guy and you partition this guy at random. So for every vertex, you choose one of the k colors with probability 1 over k. And then with high probability, the clique has actually translated into a multicolored clique. Repeat this reduction, something like, I don't know, e power k times or whatever, to get, yeah.
You will get a Turing reduction.
You will get some. You'll get parallel instances, at least one of which will work with high probability if the original guy is. And in fact, you can even de-randomize it, and you can get. You can use hash family. Yeah, that was the suggestion. Yeah, you can. That's what he said. You can de-randomize it, and you can actually get multiple instances, at least one of which will actually capture the clique in a colorful fashion if there was a clique originally. And I wish I'd made slides for this, but
There is a problem with that reduction, please.
yeah, you don't really need to exploit the full power of a FPT reduction. There is actually a fairly easy way of doing it. Yeah, I think you can go to the next slide. So here's an instance of clique. This is the guy you want to start with.
In different instances of the graph, the number of vertices, different instances of the graph, if there's an edge from A to B, put A to all the B's. And then if this has we color them all different colors.
Okay.
And if this has a clique of size k, then the whole graph is a colorful.
Okay. But do you really need n copies though?
K copies.
K copies. Yeah. Need k copies. Yeah, that's the textbook answer that I was looking for. So you make multiple copies of the original graph. Okay, make k copies. Okay, you're trying to get to an instance of multicolored clique, and you started with an instance of clique. Just make k identical copies of this guy. Great. Okay. So yeah, let's maybe first define the reduced graph completely. So what I'm going to do is make k copies. Okay, this picture is not complete, by the way, because there are edges between every pair. So this was getting too crowded, so I didn't bother. But anyway, so you make k copies of the graph, okay? And what you do is, this is something that, well, I mean, if you do a lot of reductions, you might actually refer to this process as mirroring. So you take, so here's one copy and here's another. If u and v had an edge in the original graph, you draw an edge between u and v, between all copies, okay? So u is going to have one copy there and v is going to have a copy here. That's going to be an edge. V is going to have a copy there and u is going to have a copy here, and that's going to be an edge as well. So every graph sort of becomes, sorry, every edge becomes a cross like that, okay, from u to v and from v to u. However, you have to typically decide, depending on the problem, what do you do with copies of the same vertex, okay, depending on the problem. So here I have multiple copies of the first vertex, for example. I could choose to make them all mutually adjacent, or I could choose to make all of them independent. Here I've not made them adjacent, and can you see why? Yeah, you will have a clique for free. If I make all the copies of u adjacent among themselves, then I have a copy, I have a clique, a multicolored clique here, no matter what instance you give me. So that's clearly not the right thing to do. So to prevent more than one copy of u getting into the clique, I actually make them independent. That will ensure that for every vertex, at most one of its copies is going to participate in any multicolored clique, okay? So between every pair of instances, you do the mirroring business, where every edge uv translates to every edge uv in the graph. So this is the first copy of u, this is the second copy of u, the first copy of v, and that's the second copy of v. So I'm going to draw these edges, okay? Now, if you have a clique in the original graph, do you have a multicolored clique here? Yeah? So you look at the vertices that participate in a clique in the original graph. Let's say we had a triangle here, A, B, and C. You just pick copies of those vertices here. Okay, the first copy of the first vertex in the clique, from the second partition you pick the second vertex of the clique, from the third partition you pick the third vertex in the clique, and so on, until you have exhausted all partitions. Okay, so you have k partitions, from each you have exactly one vertex, and that's definitely going to form a clique, because suppose an edge was missing, then that's like a u1 and a v2 which has a missing edge. But you look at these vertices in the original graph, they were supposed to be a part of a clique, so there was an edge there, so there's definitely an edge here. Okay, so that's the forward direction. If you had a clique, you would have a multicolored clique here. On the other hand, if you have a multicolored clique here, then what do? You know that two copies of any given vertex are not going to participate, so you actually have k distinct vertices, all of which correspond to some original vertex. So you just stare at that set, and if that's not a clique, then that means this couldn't have possibly been a clique, right? So the translation is quite transparent. So is that clear? Okay, so that's our first example of the FPT reduction. And like I said, multicolored clique is actually a useful starting point for several problems. So it's a useful formulation to remember. You can take it as an exercise, as a really easy exercise to show. So for example, this also shows that multicolored clique is hard when all the partitions have the same size, because here all the partitions have exactly n vertices. Okay, you can also show that multicolored clique is hard if each of the parts form an independent set, because you don't care about the structure inside the parts. I mean, yeah, here. So here in particular, it's independent. So multicolored clique with a lot of restrictions also tends to be hard, which is useful when you're trying to start from here and reduce to something else. It's also hard on regular graphs. This is not so easy to see, because if the graphs, if the degrees of the vertices were different initially, they're going to be different here. So it's not automatic from here. But if you started with clique on regular graphs, then this guy would also be multicolored clique on regular graphs. So next, let's see why clique is hard on regular graphs. At this point, we'll just shift to the board. So deregular graphs, is this visible to everybody at the back? Okay. So deregular graphs are graphs where every vertex has degree d, or exactly d neighbors. And if you restrict your attention to click on deregular graphs, it turns out that it's as hard as solving clique in general graphs. Okay? And let's try and understand why. So you start again with an instance of clique, and you're trying to bring it down to, you're trying to again morph the graph so that it becomes deregular. So if the graph was deregular to begin with, there is nothing to do, but otherwise you potentially have vertices of different degrees. So let's just concentrate on the max degree. I mean, let's just say I don't want to delete any edges, because that can be a bit tricky, because a clique is actually going to use edges in the original graph. So if I delete things, I would have to work very hard to compensate. So I'm not going to delete any edges. So I definitely have to make every degree at least as much as the max degree. Right? So there is a graph, there is a vertex V which has the maximum possible degree. Let's denote, so this G, let's just call that D. And what I'm going to try and do is make every vertex achieve this degree D. Okay, then every vertex would have the same degree as the maximum degree vertex that would make it somehow deregular. So let's look at a vertex U. So the max degree in this example is, let's say, 5. And here's a vertex, poor guy, has only 3 neighbors. Okay, so it needs 2 more to become, to be a part of the club. So how would you increase the degree?
By taking 2 non-adjacent vertices and
adding edges, right. You'll increase the degree by making it adjacent to more vertices. That's the only way of increasing the degree. But if we add edges to vertices that it's non-adjacent to in the graph, then that's again a little bit scary, because then you might actually be helping the clique problem in the reduced instance. So you may create a clique here that was never there in the original graph. So remember, equivalence is key. We need to really preserve what the property of the instance was. We need to add new vertices, right? We can't really afford to directly make it adjacent to things here, so let's add 2 new vertices, okay? So for every vertex whose degree has a discrepancy, so this guy is short by 1, I add a new vertex, and so forth. Okay, now what's the problem?
Vertexes have degree as 1, that is easily made into a D minus 1 regular graph.
That's easily...
Vertices will never be a part of a clique.
The way they are right now, they are independent. They will never be a part of a clique. But if you start making them deregular and funky stuff like that, then you might actually get a clique in this region, which you might have a hard time pulling back.
You can construct in a way that either they all form a clique or they don't have an induced.
You can construct in a way that they all form a clique or don't have any
If there's
use.
a clique in them, then all of them are participating.
And does that help?
number of vertex on the top could be proportional to the number of edges in the graph. So the large size clique which we will make could be just function of number of edges.
Right. So right now where we are at is that we have successfully enhanced the degree of every vertex to D, and that's good news. However, we have created these new vertices which are pendant, meaning they're degree 1. They certainly don't affect the equivalence, because you can always argue that any serious clique on at least 2 or 3 vertices will not involve these guys, because these guys don't see anybody else here. So if you involve one of these guys, you cannot pick more than 2 vertices here, because then you don't have a clique. So if you pick this guy here, you're really stuck with a clique of size at most 2. So, well, I mean, if the size of the clique you're looking for is at most 2 in the original graph, then just resolve it easily by checking if there is an edge. So let's just assume that k is at least 3. In that case, these top guys will never interfere with a clique. Okay? So equivalence is kind of okay, but you don't have the structure that you want. These guys are short on degree. So here's the graph that I had to begin with. This is G. And we just saw one trick in the previous reduction, which, well, I mean, just conceptually may be useful. I'm not talking about mirroring, talking about something more basic.
So we can add copies and then we'll be connecting this new pendant vertices to their pendant.
Exactly. So this is, let's call this G1. And these guys now need D minus 1 more degree. So just make d minus 1 more copies of G. Okay, make d minus 1 more copies of G, and for each pendant vertex, allocated the responsibility of the same set of vertices across all the copies. Is this making sense?
This is precisely what you said, right?
You're making D-size cliques.
But then you would make a click, right? Involving these mirrored copies.
I'm not mirroring anything. I'm just making independent copies. So we are not adding any edges beyond making copies. So let me draw it to. Don't have space for making K copy. Okay. So here's conceptually here is G2. GD. And here's this vertex U. Here's this copy of U, right? Because it's a copy, U has, again, degree 3 in this copy as well. And it also needs to enhance its degree, but now it's going to appeal to the same two vertices.
So this one doesn't have a pendant.
This one doesn't have its own pendant. They appeal to the same set of pendants. So these vertices, they're no longer pendant. So there's a global set of fixative vertices, okay, and they're going to be fixing d copies of the graph G. So each of them needs to give out 1 degree to fix this guy. So they're going to fix d graphs. So they're going to have degree d, okay. Is that clear? These guys are going to have degree d on top. Each of these guys have gotten their fix from the heavens above. So everybody here is d-regular as well. Everybody below, okay. So now it's a d-regular graph. But now does the clique translate correctly?
Because the new vertices will not participate in
Right. Right. The clique will be fine. It'll survive in its own copy of the graph, especially in the reverse. So let's do it a little more precisely. So if G has a clique S, that clique is certainly there right here because G is preserved as is. Yeah, completely intact. So that clique we have not touched. So the forward direction is completely straightforward. But suppose this reduced graph, let's call it H, has a clique. Has a clique S, again of the same size K. First of all, can S be spread out across 2 copies? Can S kind of split across the copies that we have made? No, because we have not added any edges whatsoever between the copies. So if S picks a vertex from here and a vertex from here, there's a non-edge in the clique. So that's not going to work. So can it involve any of the pendant vertices? For the same reason. These guys are completely independent among themselves. So if it picks something here, it can pick at most 1. And then what else will it pick? It has to pick something from one of these guys. It'll go and pick something, it cannot pick anything more. Like we argued, there is no way of involving a triangle with this vertex because it sees exactly one neighbor down below. Okay? So the clique cannot interfere with the fixative vertices in any serious way. So the clique must be sort of cocooned in one copy. So all the k vertices are coming from one copy, but hey, this is the intact copy of the graph, so it must have been there in the original graph as well.
Okay, just one question. Why did we really need the pendant in this first copy? We could have connected U to the Q here and another to there, and sort of made up for the discrepancy.
It's quite possible that you could have done something like that, but it's probably going to be harder to argue that the clique translates because now, when the moment you add edges across copies, you can have things going across.
But you won't still have these edges, right? Between going from one copy to another. So that will prevent a clique from being spread out.
Okay, so what's your suggestion again? You want to?
Instead of having those two pendants,
Right.
you can connect the U here to the one of the U's here.
But all the U's will form a
Then all the U's will form a clique. I mean, it'll at least form a D clique.
No, but you don't have a connection between this U and that U.
Well, you're going to do this uniformly, right?
Or this U is connected to each of the U's.
U's. And then what do you do to fix the degree of these U's? I mean, now this U has 1 extra degree.
Okay.
And besides, you will need to make a non-uniform number of copies because this U needs 2 more, this guy needs 1 more, somebody else needs 5 more. So you need,
You don't have a fixed number
yeah,
of
it's not a
copies.
fixed discrepancy. That's another small issue. But is the correctness of this reduction clear? Okay, so if clique on d-regular graphs is no easier than just solving clique in general. this also implies that independent set on deregular graphs is hard, because how do you go from clique to independent set? You complement a regular graph, you get a regular graph, right? The degree of every vertex is d. In the original graph, after complementation, it becomes n minus d. So, talking simple graphs here. Okay. And in fact, the multicolored versions of both of these problems are also hard on regular graphs for the same reason. The same reduction goes through. Okay, let's stare at this problem now. Okay, this is kind of a generalization of the vertex cover question. So, sorry? Was that S or yes, sir?
Yes,
What is S? S is just a number, yes. Sorry, it's a handwriting issue. I'm saying this is parameterized by S. That's what I mean. It's not a subset. So, yeah. Is there a subset X of size at most K that covers at least S edges? Okay. This is a generalization of vertex cover. In vertex cover, you're very demanding. You're saying, is there a subset of size at most K that covers all the edges? But suppose there's no vertex cover of size at most K that covers all the edges, and your budget is kind of fixed, you're tight. So then you want a subset that covers as many edges as possible, right? You want to maximize the number of edges that you can cover. Okay. Now, the claim is that this generalization of vertex cover is kind of hard, which is why it's in this lecture. So there's no point asking you to guess. So let's try to go from.
Shouldn't you do parameters both K and S?
Shouldn't we have both K and S? If you have both K and S, I mean, if I allow you to go by K, then I think you can just do the standard branching. And at the end, you would have enumerated, well, actually, you cannot quite do the standard branching, I'm sorry. Because, well, the standard branching says if you have an edge, you must pick either this or that. That's not quite correct. Because now you only are interested in covering at least S edges. I'm actually off the top of my head, I don't know. Saket would know what happens if you parameterize by both K and S? It is FPT. Okay. Probably it's not completely obvious to me, but we can think about it. Okay. Okay, so okay, at least it's non-trivial. So okay, so maybe something to think about. If you parameterize by both K and S, then you can manage FPT. But parameterized by S alone, okay, we have an issue, and let's explore that. Let's just say. Let's do independent set on deregular graphs. We know that independent set on deregular graphs is now a hard problem. So let's try to go from there to somehow partial vertex cover. Okay. Let's just try to think about this for a minute again. What if you have an independent set of size K? Okay. What if you have an independent set of size K in a graph where every vertex has degree D? What if I try to treat this guy as a candidate partial vertex cover? How many edges is it covering? At most k into d, or exactly k into d. Okay. The only way, so typically any set is going to cover at most the sum of its degree many edges. Okay. And why is it at most? The edges that you lose are the edges that get induced by the set, because those get overcounted somehow. But there's no overcounting going on here because the set is independent. So you know that there are no edges inside. So you're covering actually exactly d times k edges. Okay? So if you have an independent set of size k, then you have a partial vertex cover of size k covering at least d times k edges. Okay? All right. Now if you have a partial vertex cover of size k that covers at least d times k edges.
Why not exactly?
Okay, exactly. Fine. I mean, yeah. In this case, I mean, it is exactly d times k, therefore you have what you want. You're covering at least d times k. That's all. I'm just trying to fit it into the question. That's all. Now you're using k vertices to cover at least d times k edges. That's the partial vertex cover solution. I claim that this partial vertex cover must be independent. Why is that? I haven't changed the graph. Notice that the reduced graph I claim is exactly the same. So this graph continues to be deregular. So if there is a set that's covering d times k edges, it cannot afford to have an edge inside.
If it has, then it must have degree d plus 1.
Exactly. I mean, if it has and it's still covering d times k edges, then you violate the degree. Okay. So, or the yeah, I mean that's right. So if every vertex has only degree d to give out to cover at least d times k edges, all of these degrees must be going out. Okay. If anybody chooses to have a neighbor inside, then you fail to cover at least d times k edges. Okay. So if you have a partial vertex cover of size at least dk, then you go back. Well, a partial vertex cover of size k covering at least d times k edges, then you go back to an independent set of size k. Okay.
So parameterized by the number of edges to be covered, it turns out to be R.
Parameterized by the number of
Solution size.
parameterized by the solution size.
No,
Sorry.
parameterized by, this is the number, S is the number of edges.
Yeah,
to be
S is the
covered,
number
right?
of edges. Wait, I mean, chances are that I've made a mistake. 1 second. So what did we parameterize by here and here? So the k in the independent set goes to no.
It remains k.
It remains k. It remains k. It remains k. So you get a partial vertex cover instance g, comma k, comma d times k, starting from an independent set instance g, comma k, which is hard for. Okay, I mean, do I want to treat d as a fixed constant? The parameter is okay. I mean, actually yes. Yeah, I think I want to take this to be the solution size. Sorry, that was a hasty mistake. So if the parameter is the solution size, then k goes to k. Right?
With S, I guess it's really easy, right?
With S, is it easily easy? Sorry. I mean, the reduction has this sticky dependence on d, which I don't. Yeah, sorry. It's FPT parameterized by S. By S alone. Yeah.
What is the parameter?
Partial vertex cover. Yeah. I mean that was just, I don't know. It's kind of a typo. So I didn't mean S. I meant that the solution size, when you parameterize by solution size alone, are there at most k vertices that cover at least S edges? Then you can reduce independent set parameterized by k on deregular graphs, some arbitrary but fixed d. You can reduce it here. Okay, but it's because d is arbitrary. I mean, clearly independent set on constant values of d is not hard, right? I mean, on 3 regular graphs and so forth. Actually, independent set on 3 regular graphs is still hard, so I take that back. Okay, I mean, at least it's not. Sorry. Click, yes, sure. So no. So I take that back. But here, here, if you're just looking for an independent set of size k, that just translates to a partial vertex cover of size k in a completely straightforward fashion. I mean, the same set acts as a partial vertex cover. And the reason it's useful to have d-regular graphs is to make this argument really simple. Okay? I changed the parameter because it was wrong. I mean, I didn't mean to say that partial vertex cover parameterized by S is as hard as clique parameterized by K. Because then I would have to take K to a pure function of K as S. I mean, S should behave as a pure function of K. It's D times K. D could be order n, for example. I mean, this is not a pure function of K. Okay? So it doesn't, it's
We're not considering it as a constant here.
it's a part of, sort of a part of input.
So it could be a function of n.
It could be. There is no reason for D to be constrained by K. So this is not,
So if you fix D, it's not
D.
If you fix D, say fix D equal to 10 to the power 10, can't you solve independent set?
Yeah, in FPT time.
Because it has an independent set of size at least n divided by 10 to the power 10.
Either that, or even if you do degree-based branching, you'll be fine. If D is fixed to be a constant, right? Yeah, I mean, either a vertex is there. I mean, you can do, I mean, the standard exponential time algorithms for independent set will turn out to be FPT if D is a constant. All right. So for fixed D, you don't have hardness to begin with. When D is a part of the input, you have hardness. But then, because D is a part of the input, it's not automatically constrained by K. It could be potentially a function of n. It could be whatever you want it to be. So when I said that this is parameterized by S, that's not quite correct, because S is not turning out to be a pure function of K, but the solution size K is a pure function of K as you come down. Okay? So parameterized by solution size alone, this problem is hard. Parameterized by S or K plus S is redundant. Parameterized by S alone even, the problem is FPT. So you don't have a hardness result there. Okay? So my bad. Okay, let's quickly do another example showing the dominating set, which is another classic problem. Is also hard. And again, let's try to start from just multicolored independent set. Okay. Right. So now, what do I really want? I want the independent set to somehow translate to a multicolored independent set to somehow translate to a dominating set. Okay. This is.
Are you taking the graph to regular?
No, not really. I don't need it to be. I mean, I'm not going to infer anything more by making it regular. Okay, so what's the dominating set problem? an example of a dominating set. Dominating set is just a subset of vertices that hits all the close neighborhoods in a graph, meaning that for every vertex, either the vertex is there in the dominating set or it sees somebody in the dominating set. So it either has a friend in the dominating set or it itself belongs to the dominating set. Notice that every vertex cover is almost automatically a dominating set. Okay. Someone's not happy. Okay, so if you have a vertex cover, every vertex outside has a friend in the vertex cover, provided it had at least one edge to begin with in the graph, right? So with the exception of isolated vertices, so if you have no isolated vertices in the graph, then a vertex cover is a dominating set. Is a dominating set always a vertex cover? Not necessarily. I mean, even in this example, you have an edge that's left out, although the vertices are dominated. And remember, we talked about hereditary, non-hereditary when we were doing iterative compression. So this is one example of a problem where definitely just because a subgraph is a no instance doesn't mean that the entire graph is a no instance. You can get domination from outside. So it turns out that domination is actually a harder problem to solve compared to vertex cover, and we will try to build up to that. And that will probably be the last example that we do. Okay, so we want to somehow make an independent set dominate everything. So the crucial thing is to sort of encode. I mean, of course, one issue is that, I mean, what are we going to do? I mean, to keep everything, to keep the parameter translation under control, let's just say that the simplest thing that we will try to do is to actually take the independent set and make it act like a dominating set. Okay. Now, first of all the guys in these paths will need to be dominated. Okay. But let's say you started with an independent set where each partition was also independent, then that's not going to happen. But you can make each part whatever you like. Okay, so in particular, I could, for instance, make it a clique, then no matter what I pick, everything gets dominated. But that's a slightly bad idea because then no matter what I pick, everything will get dominated. Okay, so now I want to pick, so I want to make sure, first of all, that you're forced to pick one vertex from each part. So the dominating set cannot afford to leave out any part. It has to pick. Right now that's not true because you have edges going across. So it's possible that you can pick things from here, there, everywhere. Okay. So remember that the crucial thing is that when somebody gives you a dominating set on the reduced instance, you want to be able to pull out an independent set from it, and a multicolored independent set. So you have to work on making sure that the dominating set actually picks one vertex from each part, and that the dominating set is actually independent in the original graph. So these are the two things that we have to ensure. Okay. One easy way of forcing the dominating set to pick one vertex from each part is to sort of, so these are again in reduction terminology, these guys are called guard vertices or whatever. They guard the part and they say that, hey, a dominating set cannot afford to ignore this part. Okay. So I'm going to create a couple of vertices that are global to just this part. Okay, so for V1, I will create X1 and Y1. Okay, so who are these guys dominated by? They're dominated by the guys in this part. Okay, if you don't pick, okay, why do I need two vertices? So for example, if I just had X1 for this part, so X1 is dominated only by vertices in V1, but it's also dominated by itself. So I could pick X1 itself in the dominating set. But I'm looking for a dominating set of size, let's say I'm looking for a dominating set of size K, or even at most K. I mean, that's the question, is there a dominating set of size at most K? Okay, so now once I do this for every part, any dominating set now must have the property that it picks one vertex from each part. Do you see why? Because suppose not, right? Suppose not, and it leaves out V1 entirely. It doesn't pick anything from V1. Somehow, everything that you pick from everywhere else dominates everything in V1. Okay? But who is going to dominate X1? Maybe X1 itself dominates X1. Okay, and that's fine. But then who is going to dominate Y1? Again, you have to pick itself. If you're not going to pick anything from V1, you have to pick Y1. Okay, that means that you've used up a budget of 2 for V1 alone. But for every path, so basically for this entire region, you need to pick at least one vertex from here.
That's why you need two of those.
Yeah, I mean, you'll actually end up needing more. So, okay, I guess this is the easiest way of saying it is that from V1 union X1 union Y1, any dominating set needs to pick at least one vertex. Because X1 and Y1 are not getting dominated from anywhere else. Okay? So if you leave this out completely, then these guys just don't get dominated. Okay? So from every Vi union Xi Yi, any dominating set S has to intersect these guys at least one vertex. Okay? Because if you leave out this chunk entirely, who is dominating X1? The only guys dominating X1 are in this zone, either itself or one of these guys. Okay? So therefore, from each of these guys, you need to pick at least one. But your dominating set has size at most k. So you cannot afford to pick more than one vertex from any of these paths. Right? Because by the time you pick at least one from everywhere, you're finished. You're finished with your budget. Okay? Let's say you're looking for a dominating set of size k. So you're finished by the time you've picked at least one vertex from each part. So if you choose not to pick anything from V1, then you're forced to pick both X1 and Y1, but this you cannot afford. This is what we argued just a moment ago. If you don't pick anything from V1, then in particular you're forced to pick X1 and you're forced to pick Y1, because these guys only get dominated by either V1 or themselves. So you're forced to pick both of them, but now this is something that you cannot afford. Okay? So you have to pick something internally. You have to pick something from inside V1, and that's sort of now the dominating set is correctly spread out across all these paths. But there is no reason for this dominating set to actually be independent when you pull it back. It could be just a completely arbitrary set of vertices. Okay? All right. So let's try and force the dominating set to actually be independent. Let's look at a pair of partitions, Vi and Vj. And let's say you have a vertex here, A and B, that formed an edge in the original graph. We want to prevent the dominating set from picking A and B together. This is what we want to achieve, right? So now you have to say that if the dominating set picks both A and B, there is a contradiction. Of course, you have to do something to achieve this. What can possibly go wrong? What can we try and make go wrong? We have domination. The problem is domination. So we have to say that if you pick both A and B, then there is something that gets left out. There's something that goes undominated. Okay? And that's specific to this edge. Okay? So let's now add, again, a guard vertex for this edge that's going to say, hey, if you choose to pick this edge, you're going to leave me out, certainly. We have already ensured that the dominating set is compelled to pick exactly one vertex from each part. It cannot afford to do any more or any less.
A has at least one neighbor, it won't be dominated in V1.
If
A has at least one neighbor, it won't be dominated in V1. It has to be dominated in V2.
this guy has at least one neighbor, sorry.
So are you putting edges between the, if there is an edge from A to B, are you putting it in every copy of the thing, or are you?
No, this is an arbitrary fixed instance now. I mean, I have no control over. I mean, I guess you could work with the copied version where the edges reflect. But what's the idea? Okay, just one second. The partitions are V1 to Vk. No, the partitions are given to us. Remember, we're reducing from independent set, from multicolored independent set to dominating set. And in dominating set, we have no obligation to provide a partition. We can just give a completely uncolored graph. And that is why we did some work in ensuring that the dominating set respects the form of the multicolored independent set. Because now I'm going to output an uncolored graph, and the dominating set problem nowhere says pick one from this, pick one from that. There's no such thing in the definition. The dominating set is just going to go and pick some k vertices. By doing this, we have ensured that the k vertices that it picks, I mean, if you manage to find a dominating set, those k vertices must necessarily be spread out across all the paths. There is no way that it can avoid doing that. And now we are going to force it to have some more structure. In particular, we are going to ensure that If the dominating set chooses to pick vertices in a particular way, then those vertices couldn't have been adjacent in the original graph, which will then complete the reverse direction of the reduction. Hmm. From Vi to that vertex. So there is somebody here who doesn't have an edge from A. But this guy can be dominated from elsewhere in the graph. So there's no reason to believe that the vertices in Vj are going to be dominated only by vertices from Vi. This guy has not taken the responsibility of Vj, so vertices in Vj can be getting dominated from all over the place. Okay? And besides, if you try and rely on, forcing this edge by relying on the structure of the input graph, I'm not saying you cannot do it, probably there's a nice way of doing it, but intuitively, the structure of the given graph is kind of arbitrary beyond the partitioning, right? What's going on across these paths, we don't have much control. So if you do it that way, like I said, potentially you can do it, but chances are that the proof is going to be a little more messy. And since we are gadgeting after all, we have the freedom to add more stuff to force more things. So let's try and do that. So let me add a gadget for the edge AB alone. That'll take care of AB. Okay. Let me add WAB. Okay. And what I'll do is I'll make this guy incident to everything in Vj except for A. I'll make it incident to everything in Vi except for A, everything in Vj except for B. Okay, so from Vi and Vj, once you've committed to picking A and B, you cannot pick anything else because you've exhausted your budget. But here's this guy who is dominated by everybody except for A and B.
We put it after we pick A and B.
Yeah.
Correct. After you pick A and B. So what I'm doing, I'm just reverse engineering the reduction in the following sense. I'm saying what I want is that in the graph that I generate, when I run a dominating set algorithm, if the dominating set algorithm goes and picks two vertices that formed an edge in the original graph, then it cannot be a dominating set. That's what I want.
So what you're saying is for every pair of edges like A and B, you have a vertex like W.
That guards that edge. That's a part of the graph that I'm creating.
Yes.
So when I create,
Yeah,
exactly. No. I'm not doing it after the guy finds the dominating set. Okay, I'm sorry if that was the confusion. I said if a dominating set picks A and B, it's going to lose out. But I'm going to do this for every edge in the graph. Of course, for every edge in the graph, which goes across. That's right. For every edge in the graph that goes across, I'm going to add, because in any case there were no edges to begin with within the path, so there's nothing to do there. So for every edge that goes across, I'm going to add a vertex. Think of it as a vertex that's sort of the parent of this edge. It's taking care of this edge. It's making sure that the dominating set doesn't go and pick both endpoints of this edge. Because if the moment a dominating set does that, it misses out on this vertex, which it cannot afford to do. Okay? The only way it can dominate this vertex is by avoiding one of A or B.
Will force one of them, right?
It will force one of A or B? No, because, why? Because both A and B are not dominating this guy. Anybody else from here will dominate this guy. Okay? So all you need to do is pick at least one vertex that's not A or B, and you've dominated this guy. Okay? So it doesn't force one of A or B.
So couldn't I pick A and WAB as part of the dominating set?
You could, but then you have used up one of your budget K, which means you cannot pick anything from here, but you had to pick one thing from here.
Do I need to, given that we have this thing?
No, because this guy needs one vertex in the dominating
I
set
still
for
need to cover x2, y2 and all.
exactly. So there is xj and yj that are forcing the dominating set to pick something from here. So that's a given by now. So the dominating set must intersect each of these
What if I
partitions.
have an edge between,
A edge
if I
between.
have say x number of vertices in Vi and x in Vj, and I have x edges running across.
Sure. If you have lots of vertices, you're going to have lots of these gadgets. So how many WAB vertices are there on top? So let's do the big picture of the reduction.
What I'm saying is following. So I have x edges on x vertices in Vi
Okay.
and x number of vertices in Vj.
Okay. And there's a matching
I have a
of.
perfect matching kind of.
Okay.
I have
Sure.
then you cannot pick anybody, right? What does that mean?
No, all it's saying is that you cannot pick A and B simultaneously. Okay, so if you have a perfect matching, you're just
I
saying,
see.
I mean, there's nothing stopping you from picking this guy and this guy, right?
But the A is going to do everything and B just picked up.
Not really, because if you have VI, there are these